Combining waves of equal period. A sinusoidal function of the form f of x equals a sine of bx plus c can be rewritten using the sum of angles identity. Example 5. Rewrite f of x equals 4 sine of 3x plus pi divided by 3 as a sum of sine and cosine. Using the sum of angles identity, evaluate the sine and cosine, distribute and simplify. Notice that the result is a stretch of the sine added to a different stretch of the cosine, but both have the same horizontal compression, which results in the same period. We might ask now whether this process can be reversed. Can a combination of a sine and cosine of the same period be written as a single sinusoidal function? To explore this, we will look in general at the procedure used in the example above. F of x equals a sine of bx plus c, use the sum of angles identity, equals a of sine of bx multiplied by cosine of c plus cosine of bx multiplied by sine of c, distribute the a, equals a sine of bx multiplied by cosine of c plus a cosine of bx multiplied by sine of c. Rearrange the terms a bit, equals a cosine of c multiplied by sine of bx plus a sine of c multiplied by cosine of bx. Based on this result, if we have an expression of the form m sine of bx plus n cosine of bx, we could rewrite it as a single sinusoidal function if we can find values a and c, so that m sine of bx plus n cosine of bx equals a cosine of c multiplied by sine of bx plus a sine of c multiplied by cosine of bx, which will require that m equals a cosine of c, n equals a sine of c, which can be written as m divided by a equals cosine of c, n divided by a equals sine of c. To find a, m squared plus n squared equals a cosine of c squared plus a sine of c squared equals a squared multiplied by cosine squared of c plus a squared multiplied by sine squared of c equals a squared multiplied by cosine squared of c plus sine squared of c. Apply the Pythagorean identity and simplify, equals a squared. Rewriting a sum of sine and cosine as a single sine. To rewrite m sine of bx plus n cosine of bx as a sine of bx plus c, a squared equals m squared plus n squared, cosine of c equals m divided by a, and sine of c equals n divided by a. You can either use either of the last two equations to solve for possible values of c. Since there will usually be two possible solutions, we will need to look at both to determine which quadrant c is in and determine which solution for c satisfies both equations. Example 6. Rewrite 4 multiplied by the square root of 3 sine of 2x minus 4 cosine of 2x as a single sinusoidal function. Using the formulas above, a squared equals 4 multiplied by square root of 3 squared plus negative 4 squared equals 16 multiplied by 3 plus 16 equals 64, so a equals 8. Solving for c, cosine of c equals 4 multiplied by the square root of 3 divided by 8 equals the square root of 3 divided by 2, so c equals pi divided by 6, or c equals 11 pi divided by 6. However, notice sine of c equals negative 4/8 equals negative half. Sine is negative in the third and fourth quadrant, so the angle that works for both is C equals 11 pi divided by 6. Combining these results gives us the expression 8 sine of 2x plus 11 pi divided by 6. Rewriting a combination of sine and cosine of equal periods as a single sinusoidal function provides an approach for solving sum equations. The product to sum and sum to product identities. Identities. The product to sum identities. Sine of alpha multiplied by cosine of beta equals half multiplied by sine of alpha plus beta plus sine of alpha minus beta. Sine of alpha multiplied by sine of beta equals half multiplied by cosine of alpha minus beta minus cosine of alpha plus beta. Cosine of alpha multiplied by cosine of beta equals half multiplied by cosine of alpha plus beta plus cosine of alpha minus beta. We will prove the first of these using the sum and difference of angles identities from the beginning of this section. The proofs of the other two identities are similar and are left as an exercise. Proof of the product to sum identity for sine of alpha, cosine of beta. Recall the sum and difference of angles identities from earlier. Sine of alpha plus beta equals sine of alpha multiplied by cosine of beta plus cosine of alpha multiplied by sine of beta. Sine of alpha minus beta equals sine of alpha multiplied by cosine of beta minus cosine of alpha multiplied by sine of beta. Adding these two equations, we obtain sine of alpha plus beta plus sine of alpha minus beta equals 2 sine of alpha multiplied by cosine of beta. Dividing by 2, we establish the identity. Sine of alpha multiplied by cosine of beta equals half multiplied by sine of alpha plus beta plus sine of alpha minus beta. Example 8. Write sine of 2t multiplied by sine of 4t as a sum or difference. Using the product to sum identity for a product of sines, sine of 2t multiplied by sine of 4t equals half multiplied by cosine of 2t minus 4t minus cosine of 2t plus 4t. If desired, apply the negative angle identity. Distribute equals half cosine of 2t minus half cosine of 6t. Identities. The sum to product identities. Sine of u plus sine of v equals 2 sine of u plus v divided by 2 multiplied by cosine of u minus v divided by 2. Sine of u minus sine of v equals 2 sine multiplied by u minus v divided by 2 multiplied by cosine of u plus v divided by 2. Cosine of u plus cosine of v equals 2 cosine of u plus v divided by 2 multiplied by cosine of u minus v divided by 2. Cosine of u minus cosine of v equals negative 2 sine of u plus v divided by 2 multiplied by sine of u minus v divided by 2. We will again prove one of these and leave the rest as an exercise. Proof of the sum to product identity for sine functions. We define two new variables, u equals alpha plus beta, v equals alpha minus beta. Adding these equations yields u plus v equals 2 alpha, giving alpha equals u plus v divided by 2. Subtracting the equations yields u minus v equals 2 beta, or beta equals u minus v divided by 2. Substituting these expressions into the product to sum identity, sine of alpha multiplied by cosine of beta equals half multiplied by sine of alpha plus beta plus sine of alpha minus beta gives sine of u plus v divided by 2 multiplied by cosine of u minus v divided by 2 equals half of sine of u plus sine of v. Multiply by 2 on both sides. 2 sine of u plus v divided by 2 multiplied by cosine of u minus v divided by 2 equals sine of u plus sine of v, establishing the identity. Example 9. Evaluate cosine of 15 degrees minus cosine of 75 degrees. Using the sum to product identity for the difference of cosines, cosine of 15 degrees minus cosine of 75 degrees equals negative 2 multiplied by the square root of 2 divided by 2 multiplied by negative 1/2 equals square root of 2 divided by 2.